with the recent development of the MTW tensor of Gabriel and Zhang, and we first will see the video.
Today I'll be talking about the regularity theory of optimal transport. The goal of this talk is to give a brief introduction to the history of this problem and to indicate some current areas of research. Before I get started, I'd like to thank the organizers of this session for giving me the opportunity to speak. Optimal transport was introduced by Gaspard Monge in 1781. In its original formulation, the central question was the following. We are given a pile of stone or some other raw material and must use it to build a castle. In order to do so, we need to move, that is, transport, the stone from the pile to the worksite. We want to find the most efficient way to move the rock so as to minimize the total amount of work we need to do. In this problem, Monge assumed that each part of the stone pile would be sent to a unique part of the castle. In other words, the transport would be induced by a map from the pile to the castle. To formalize this problem, we use the Kantorovich formulation of optimal transport. For this, we consider the stone pile and castle as probability spaces x mu and y nu. Here, the probability measures describe the shape of the distributions. To encode a transport, we consider a coupling of the measures mu and nu, which we denote by pi. I should tell you what a coupling is. A coupling of two probability measures is a measure on the product space so that the marginal distributions are mu and nu, respectively. In other words, if we integrate pi with respect to y, so what remains is a distribution on x, the resulting measure is mu. And similarly for nu when we integrate with respect to x. To obtain the transport from the coupling, we consider the disintegration of pi with respect to x and distribute the mass according to this disintegration. Intuitively, the disintegration gives the conditional distribution of pi for a fixed x value. In general, the point x might be a set of measures 0, so we need to use the disintegration instead of the conditional distribution to make this precise. What we can see, however, is that the mass at a point x is split apart and distributed throughout y. In order to discuss optimal transport, we also need a cost function, which is the cost of moving mass from a point in x to a point in y. Monge supposed that the cost of moving a unit of mass from a point x to a point y is the distance between x and y. However, for many applications, it's preferable to use the square distance cost instead, which is what we'll do for most of the rest of this talk. With these preliminaries out of the way, we can now discuss the Kantorovich problem of optimal transport. This problem tries to find a coupling pi naught which minimizes the total cost of the transport. Here, capital pi of mu nu denotes the space of all couplings between mu and nu. The advantage of considering this framework is that for very general costs and measures, an optimal coupling exists. Furthermore, Kantorovich showed that there is a dual formulation to this problem, and it's possible to solve the dual problem using linear programming. For this work, Kantorovich was awarded with a Nobel Prize. However, in general, the solution to the Kantorovich problem may split mass, and so not solve the Monge problem. For instance, if mu has atoms, but nu is Lebesgue absolutely continuous, there will be a solution to the Kantorovich problem, but there are no transport maps at all. As such, the existence question for the Monge problem remained open for a long time. This question was finally solved by Bernier in 1987 for the square distance cost, and a few years later, Gangbo and McCann generalized Bernier's results to consider arbitrary cost functions. But as you can see, the full statement of this theorem is fairly involved. In the context of Monge's original question, we can state it a bit more simply. If the stone pile and castle have the same dimension, the measures mu and nu are suitably well behaved, and the cost function c is smooth and non-degenerate, then the solution to the Kantorovich problem is actually a solution to the Monge problem. In other words, it doesn't split mass. Furthermore, the transport is given by the c subdifferential of a potential function u, which satisfies a particular PDE known as the Jacobian equation. Before moving on, there's a few points I should note. First, the potential shown here is not U, so this should be considered as a heuristic diagram instead of a precise picture. Second, for the square distance cost, the C exponential terms, which appear in the Jacobian equation, correspond to the usual exponential map on a Riemannian manifold. And finally, Monge's original cost function does not satisfy the third hypothesis of this theorem, which is one of the main reasons why the square distance cost is preferable. Now that the question of existence for the Monge problem has been settled, the natural follow-up question is whether the solution is somehow continuous. In other words, do blocks of stone which are close together in the pile get transported to nearby parts of the castle? Using the previous result, we can solve this question by analyzing the Jacobian equation, which is a fully nonlinear degenerate elliptic partial differential equation. In particular, we can solve this question by finding a priori estimates for the solutions of the Jacobian equation. For this type of equation, the weak solutions will be uniformly Lipschitz, which implies that they are differentiable almost everywhere. However, in order to find a Lipschitz estimate on the transport, what we need is a C2 estimate on U. To put that more concretely, we want to show that the potential cannot have corners. Unfortunately, without making some additional assumptions on the costs and measures, this is not possible to do. For instance, if X is connected but Y is disconnected, there are no continuous transport maps at all. Continuity can also fail even when there are no topological reasons preventing it. For the square distance cost, Caffarelli showed that if we take the uniform measure on the disk and transport it to the uniform measure on a barbell, there are two segments, one at the bottom and the other at the top of the disk, where the transport is discontinuous. More conceptually, this shows that non-convexity of Y is a global obstruction to regularity. In other words, when Y is not convex, we can always find smooth measures mu and nu for which the transport has some discontinuities. However, the situation is not completely hopeless. For the square distance cost in Euclidean space, the Jacobian equation simplifies considerably to a more familiar Monge-Ampere equation. And using PDE techniques, people were able to study this equation and show that the transport is in fact continuous under various assumptions on the measures and with the additional assumption that Y is convex. However, for more general cost functions, the regularity problem remained completely unsolved for another decade. Then, in 2005, a breakthrough was found by Ma, Trudinger, and Wang. In particular, they found conditions on the cost and measures to ensure that the transport is continuous. As you can see, this is a very technical theorem. However, from a high-level perspective, we can summarize it as follows. If the cost function is non-degenerate, the measures are sufficiently smooth, the domains x and y satisfy some type of convexity condition, and the so-called MTW or MTW0 condition holds, then the transport is continuous. Three of these hypotheses should look familiar. However, there's one that is completely new, and that's the one that we'll focus on now. In order to discuss the MTW condition, I need to first explain the notation. The terms with C and subscripts correspond to derivatives, with the indices before the comma being x derivatives and those after being y derivatives. For instance, C sub I, j, comma p is a third partial derivative of C with respect to xi, xj, and yp. To define the C sup ij terms, we consider the mixed Hessian partial xi, partial yj of C. We then expand that into a matrix of second derivatives and compute the inverse of this matrix. Each component of the inverse matrix is C superscript I, comma j. It's worth noting that we can always compute this inverse matrix because the first assumption of the MTW theorem is that the mixed Hessian is invertible. We then take two orthogonal vectors, eta and z, whose components are eta1 through eta n, and z1 through zn, respectively. Finally, we combine all of these terms into the expression given above, where the sum is taken from 1 through n for each of the indices. The cost function satisfies the MTW condition if the result is always non-negative, no matter which orthogonal vectors we use. To simplify this condition, it is helpful to consider the MTW tensor, which is defined to be the expression on the left-hand side of the MTW condition. We can immediately see several properties of this object. First, it is fourth order, since the term c sub ij comma rs involves 4 derivatives of the cost function. Second, it is nonlinear, since the first term involves multiplying several third derivatives and inverse matrices, which is a very nonlinear process. Third, it is non-local, in that in order to compute it, we need to be able to calculate the cost function both in a neighborhood of x as well as y. It's not sufficient to calculate it in a neighborhood of x alone for a fixed y value. Finally, and much less obviously, it turns out that this quantity is tensorial, so long as we interpret eta as a covector and thus require that eta of z is 0. This analysis shows several basic properties of the MTW tensor, but doesn't explain its geometric meaning or the role it plays in optimal transport. At first, MTW non-negativity appears to be a strange and complicated assumption. So in order to understand it, we must find another way to think about the MTW tensor. In 2009, Wilper studied this question and found a geometric interpretation of the MTW condition in terms of convex analysis. By doing so, he showed that the MTW tensor provides a local obstruction to regularity. In other words, if the MTW condition fails, even for a single pair of vectors, we can find smooth measures mu and nu, with convex supports, whose optimal transport has discontinuities. Furthermore, he showed that for the square distance cost on a Riemannian manifold, the MTW tensor on the diagonal is proportional to the sectional curvature. This shows that the MTW condition is a non-local strengthening of non-negative sectional curvature. Today, the study of optimal transport on Riemannian manifolds is a large and active field. This work has shed new light onto the global geometry of manifolds, especially those of positive curvature. Unfortunately, describing this work in any detail would take me much longer than 20 minutes, which is why I've only mentioned it in passing. Another interpretation of the MTW tensor was found by Kim and McCann, this time in terms of pseudo-Riemannian geometry. They considered the space x times y and used the cost function to induce a signature NN pseudometric. In this geometry, the MTW tensor becomes the curvature of certain light-like planes. Doing this immediately explains some of its fundamental properties, such as why it's a tensor. There are other geometries which can be associated with optimal transport as well. For instance, for costs which are induced by a convex potential, there is also an associated Kähler geometry. More precisely, it is possible to construct a Kähler metric whose curvature encodes the MTW tensor. In this case, it is also possible to understand relative convexity in terms of conjugate connections from information geometry. This shows that there are some interesting connections between optimal transport, on the one hand, and complexer information geometry, on the other. More generally, this line of work to better understand the geometry of the MTW tensor gives insights into the regularity theory, which allows us to more fully understand the behavior of optimal transport. It also highlights some unexpected interplay between geometry and analysis, which has applications in other areas of mathematics. In this spirit, let me conclude this talk by posing an open question about the behavior of the MTW tensor under Ricci flow. Does the Ricci flow preserve the MTW zero condition? In other words, given a Riemannian manifold whose square distance satisfies MTW0, is it necessarily the case that all future metrics also satisfy MTW0? I suspect that the answer is positive, at least in dimensions 2 and 3, but in higher dimensions it might be necessary to make a stronger assumption on the curvature, such as non-negative curvature operator. In any case, I'd be interested to know the answer to this question, because it gives some sense of whether the Ricci flow can preserve non-local curvature conditions. Thank you for listening.
So, thank you. I can tell you that the audience was in deep silence when listening to the last part of your talk because your voice was fading in the recording. But it's just a technical issue, no worry. So
there is no question and he's not connected. So he will not be able to answer your questions.
So we can ask a question, but you have to answer. Trudinger, wrong theory. I can answer.
We will move on to the next presentation then.
Yes. And if there is he's connected, then hold on your questions. I'll beat some. Okay. So due to the fading of the current speaker, we go to the next presentation about Wasserstein Proxima of GAN by Alex Long. Lin, Vushan Lee is co-chairing the session, Stanley Osher and Guido Montufar. Sorry if I misspelled the name. I will just first see the presentation.